Hi.
Good morning. Okay, Fatima, just tell me from where you have to start.
Can we start from thermodynamics, like the chapter?
Okay, thermodynamics. Okay, done. So in which chapter you are in school?
We are in thermodynamics. We just started.
Okay, no problem.
Okay.
First, this particular thermodynamics consists of two words, therm and dynamics. Therm means heat and dynamic means flow. So in this chapter, we mainly define the flow of heat and conversion of heat into some other form of energy like electrical energy, mechanical energy, or how to design any particular engine to convert heat energy into mechanical energy, for which various devices may act on. So thermodynamics is basically the study of flow of heat and conversion of heat into other form. Is it clear?
Yes, sir.
So to define this thermodynamics, let me give you some introductory part or some basic concept regarding it. Then I will come to the main process part. Okay. So first is thermodynamical variable. There are some physical quantity which defines condition or state of gas at any particular instant, like number of moles, pressure, volume, temperature. So these particular variable are termed as thermodynamical variable, which may define the condition of gas at any instant. Is it clear, Fatma?
Yes.
So the physical quantity on which condition of gas depends upon are termed as thermodynamical variable. Next, there is spatial relationship between these thermodynamical variable to define condition of gas at any instant related to any different process, which is called equation of state. So equation of state is a spatial relationship between thermodynamical variable to define process or condition of gas at any instant. So it is the relationship between thermodynamical variable to define process or condition of gas at any instant. So in general, P(V) to the power x equals to constant, which may be written as P raised to 1 over x, V equals to constant, or in terms of ideal gas, it may be written as PV equals to nRT. Any doubt related to this part?
No, sir.
Okay, just write it down till this.
Done, sir.
Okay. Next is molar specific heat capacity or constant. You must have learned about specific heat constant in last chapter, thermal properties of matter. Fatima, any idea what do you mean by specific heat constant?
No, sir.
Specific heat constant means the amount of heat required to raise the temperature of a specific amount of substance by 1 degree Celsius or 1 Kelvin. So in this part, we have molar specific. It means amount of substance will be in terms of mole since we are defining for gas. So we may define this molar specific heat constant as the amount of heat is required to change the temperature of 1 mole gas by 1 degree Celsius or 1 Kelvin at given condition. It means for different process of gas, it will have different value. That's why I'm defining for given condition. So this molar specific heat constant will be different for different process for the same gas. So in general, it will be equals to dq equals to n times c into dt. So c equals to dq divided by number of moles times dt, where c is called molar specific heat constant. But in general, c is equals to r by gamma minus 1 minus r by x minus 1. So this will be a generalized formula of calculating molar specific heat constant depending upon different process. Is it clear?
Yes, sir.
So in last part, I defined you about equation of state. So from this part, we have PV raised to X. So if you know the value of X related to this process, on putting this value of X in this expression, you will be able to calculate C or simply molar specific heat constant. Now, next, what do you mean by R and what do you mean by gamma? I'm defining you. Here, R is called universal gas constant. You must have learned this in chemistry. It is equals to 8.314, or for calculative part, just use 25 by 3 joule per mole per Kelvin. Fatima, is it clear?
Yes.
Next, what do you mean by this gamma? First, write it down. I'm defining you this particular gamma.
Done, sir.
This
Okay, next is, what do you mean by this gamma? So to define this, let me give you an idea about degree of freedom. Suppose you have any monoatomic gas. So if I ask you in which direction it will tend to move independently, so you'll say it may move along x-axis, along y-axis, along z-axis. And this movement of this monoatomic particle along any coordinate axis will be termed as its translational motion. Is it clear?
Yes, sir.
So we may define in how many direction this particular monoatomic particle having energy contained in it. So you'll say in 3 different directions, that is along x-axis, y-axis, and z-axis. And all 3 directions are based on its translational energy. So we call it as 3 different directions, and all are due to its translational energy. So degree of freedom simply states the number of coordinate or independent direction in which a molecule or a particle contain energy is called degree of freedom. Is it clear?
Yes, sir.
Suppose if you have to calculate number of ways for diatomic, let's say H2 molecule, N2 molecule, and any other particle. Suppose this is any diatomic molecule where particle is attached at this end and particle is attached at this end. So this particular molecule will tend to move along x-axis, along y-axis, and it may move along z-axis as well. So we can say it will have 3 different ways of its translational motion. Is it clear?
Yes, sir.
Now, whether it can rotate or not, so you'll say, yes, it may rotate along this axis. It may rotate along this axis, but there will be no rotation possible if you see along this way. Since along this axis, it will behave as point object for which there will be no rotation possible. So this diatomic molecule will have energy contained in it due to its 3 translational motion along all degree coordinate axis and 2 different rotational motion along this axis and along this axis. There will be no rotation possible through y-axis. So how many different ways of energy containing in this particle? So you'll say 3 different ways due to its translational part and 2 different ways due to its rotational part. So in total, it will have 5 different ways of energy containing. Fatima, is it clear?
Yes, sir.
Similarly, if you have to calculate for water molecule, so first define what will be the shape of water molecule, linear or something else.
Can you repeat that?
Yes.
Can you repeat what you said?
What will be the shape of water molecule, H2O? It will be bend shape, okay? Due to lone pair present on oxygen molecule, oxygen part. So the shape of water molecule will be like this. Two hydrogen and one oxygen. Is it clear?
Yes, sir.
So let's say this is z-axis. This is x-axis, y-axis, and z-axis. So this particle will move along X, Y, and Z. So it will have three translational energy part. Will there be rotation or not for this molecule? So you'll say yes, it may rotate along this way, and also along this way. So how many different rotation possible in this part? So you will say three different rotation. Is it clear?
Yes, sir.
So simply degree of freedom is the number of direction or coordinate in which a gaseous particle or molecule may contain energy is called degree of freedom. So degree of freedom is the number of ways or coordinate along which a gaseous particle or molecule may contain energy. So for monoatomic, the first one is monatomic, like helium, neon, argon. Total number of ways of energy containing is 3. So degree of freedom represented by F is equals to 3. For diatomic, such as H2 molecule, N2 molecule, O2, and so on, total number of ways of energy containing will be 3 due to its translational part and 2 due to its rotational part. So in general, it will have 5 different ways of energy containing. For triatomic or bent shape like H2O, it will have 3 translational part and 3 rotational part. So total, it will have 6 different ways of energy containing. Is it clear?
Yes, sir.
Now, according to this degree of freedom, we may define gamma as a specific gas ratio. So gamma is equals to Cp over Cp, which is equals to 1 plus 2 by F. C is molar specific heat and P subscript part to define its process. So we call the Cp as molar specific heat at constant pressure, Cv molar specific heat at constant volume. We will define this particular two word in later on for different process. So up to this part, just remember gamma is equals to 2 by 1 plus 2 by F. Is it clear?
Yes, sir.
Now, if you put the value of F according to monoatomic, that is 3. So gamma for monoatomic will be 1 plus 2 by 3, that will be 5 by 3, or it will be about 1.67. Similarly, gamma for diatomic will be 1 plus 2 by F. F is 5. So it will become 7 by 5. That will be 1.4. And similarly, gamma for triatomic, it will be 1 plus 2 by F. That will be 4 by 3. That is 1.33. Is it clear?
Yes, sir.
Now, if I ask you to arrange this particular gamma in ascending order or descending order, so which is maximum?
Can you repeat the question?
Which value of gamma is maximum for monatomic, diatomic, triatomic?
Diatomic is maximum.
No. For monatomic, we have how much?
1.67.
And for diatomic, how much?
1.4.
So which is greater?
1.4.
1.4 is greater than 1.6.
1.6. 6, 7.
Okay, so we can say gamma is maximum, then di, and then tri. Is it clear?
Yes.
So gamma for monatomic is greater as compared to diatomic and greater as compared to triatomic, and all would be always greater than 1 but less than equal to 2. So just remember this particular range of gamma for any particular molecule of gas. So is it clear up to this part? What
Yes.
do you mean by degree of freedom? How to calculate gamma, that is specific gas ratio?
Yes, sir.
Okay, just write it down.
Done, sir.
Any doubt?
No, sir.
Okay. Now, related to this part, you will be asked on what factor degree of freedom may depend upon, or simply whether degree of freedom may depend upon temperature or not. So you will say on increasing temperature, bond in between molecule will get weakened. So it will have additional vibrational energy due to increasing its temperature. Hence, degree of freedom increases. So we can say on increasing temperature, bond get weakened. So vibrational energy of molecule increases. Hence, degree of freedom increases. Is it clear?
Yes, sir.
Just one. Okay, Fatima, any doubt?
No, sir.
Okay. Hello.
So,
Okay, there was some issue. Okay, now it's clear. Okay, next is we have mainly two different types of gas. First is real gas and second is ideal gas. Do you have any idea about these two terms? Fatima?
real gas is which in which molecules occupy space.
And in ideal gas, there will be no occupying space.
Um,
Okay, let me define you. Suppose in a gas, if there is interaction between particle of gas, if there is interaction and on the basis of their interaction, it will have potential energy. So first is, if there is interaction between particle of gas, so it will have potential energy due to interaction. And you must have learned about force and gravitational force. That will be attractive force. So force that will be attractive in nature will be taken as negative, and consequently potential energy for attractive force will be negative in nature. So in this part, potential energy due to interaction between particles will be negative. Again, it will have some kinetic energy due to temperature of system. So if you add these two energy for any particular gas, it will be termed as internal energy. So internal energy denoted by U is equals to kinetic energy plus potential energy. Is it clear?
Yes, sir.
Now, in a particular gas, if there is no interaction between particles, just suppose if there is no interaction between particle of gas, so potential energy in this case will be zero. So it will have only kinetic energy due to temperature. So total energy or total internal energy in this case will be only due to kinetic energy, or you will say only due to its temperature. Is it clear?
Yes, sir.
Now, there will be a question, at what condition a real gas will tend to behave as ideal gas? So let me define you. Suppose in a vessel enclosed by piston, and there is particle initially at this point, this point, this point, and this point. So if you compress this particular piston slightly downward, so will the separation between particle increases or decreases? If you compress this particular piston slightly downward, so separation between particle increases or decreases?
Increases.
Increases. Initially, it having large volume, so large space for this particular particle in between them. If you compress it, the spacing between them decreases. So there will be lesser distance in between particle. Is it clear?
Yes, sir.
So if you expand this particular piston outward, so volume of this particular system increases. So separation between particle increases. Is it clear?
Yes, sir.
So in this part, for real gas, it will have some potential energy due to interaction. So if you increase the separation between these two particles slightly outward, so distance increases, potential energy decreases. So at that condition, it will tend slightly to behave as ideal, or it will have least interaction between particles in that case. So first, pressure should be low. Is it clear?
Yes, sir.
Next, if you increase the temperature of this particular system, so particle will have greater thermal energy. So it will have greater movement randomly in all different directions. So at that case also, there will be least interaction in between them. So in conclusion, we can say at low pressure and high temperature, real gas will tend to behave as ideal gas. Is it clear?
Yes, sir.
Any doubt?
No, sir.
So we can write at low pressure and high temperature, real gas will tend to behave as ideal gas. Fatima, just tell me why pressure should be low. Fatima?
It should be low it can so it can have like the interaction.
No. You will say at low pressure, the particle separation increases, so potential energy decreases. Is it clear?
Yes, sir.
And why temperature should be high? So you will say at high temperature, they will have more thermal kinetic energy. So there will be more movement in particle. Hence, they will have least interaction in between them. So we have to simply convert real gas into ideal gas, so for which the interaction between particle must get vanishes. So at what condition this interaction will get vanished? So you will say at low pressure and high temperature, there will be no interaction or there will be least interaction between particle. Hence, real gas will tend to behave as ideal gas. Is it clear?
Yes, sir.
Okay, just write it down.
Done, sir.
Okay. Now, on the basis of this concept, you will be asked, suppose we have equal volume of solid, liquid, and gas. First vessel containing gas, second one containing liquid, and third one having solid. And all are at same temperature. So which of these three will have greater internal energy, or which will, or no, these will have least internal energy? So you'll say internal energy will depend upon two factors. First is kinetic energy, and second one is potential energy. Since potential energy will be due to its attraction, so it will be always negative. So total internal energy will be this. Is it clear?
Yes, sir.
Now, since temperature of all these three states is same, so you'll say these all would have same thermal kinetic energy, K. In which state do you think will have maximum interaction in between particle?
Solid.
Good. So maximum interaction means maximum potential energy. Is it clear?
Yes.
So maximum amount gets subtracted with its kinetic energy. So total energy, internal energy will become least in case of solid and maximum in case of gas. Is it clear?
Yes, sir.
So we can say potential energy in this case will be maximum. Potential energy in this case will be minimum or just zero. So greater the potential energy between interaction, it will have smaller internal energy. So internal energy for solid will be least and internal energy for gas will be most than liquid than solid. Is it clear?
Yes, sir.
Okay, just write it down.
Done, sir.
Okay, next is what do you mean by system? And what do you mean by surrounding? And system and surrounding combinedly termed as universe. Is it clear?
Yes, sir.
So let me define you what do you mean by system and surrounding. Suppose in a vessel, if there is piston, enclosed by any gaseous particle. So let's say any ideal gas enclosed in this particular vessel. So system is a gas enclosed in a vessel which is under observation and for which we may calculate its pressure, volume, temperature at any instant is termed as system. So system is a gas enclosed in vessel which is under observation is called system. So what do you mean by surrounding? So you will say all the influencing factors from outside which may affect to change its any physical quantity by any means is termed as surrounding. So our surrounding is all the influencing factor from outside is termed as surrounding, and system and surrounding combinedly termed as universe. Is it clear?
Yes, sir.
So in general, this particular system may be of three types. So first is open system, second is closed system, and third is isolated system. Do you have any idea what do you mean by open system?
No, sir.
If from a system, there will be exchange of heat as well as matter between system and surrounding, then it will be termed as open system. If both energy and matter get exchanged between system and surrounding, then it is called open system. If a system allows exchange of only energy and there will be no exchange of matter, then it will be called closed system. Only energy can exchange in between system and surrounding. And for isolated system, no exchange of energy and matter can take place. Fatima, is it clear?
Yes, sir.
Okay, just write it down.
None, sir.
Any doubt up to this part?
No, sir.
Sure.
Yes.
Okay. So this is all the introductory part of this thermodynamics. So let's stop here for today. In next class, we'll start with process, different process, and next about thermodynamical laws. Okay.
Okay.
Just revise this whole part. From next class, we'll start with the main basic part of this particular whole chapter. Okay.
Yes, sir.
Okay then.
Bye, sir. Thank you.